Hello, everyone. Thanks for joining the session. My name is June, and I'm the moderator for today. Thank you for joining us to explore the latest advances in federated machine learning. I know you're calling from all over the world, and maybe for some of you, the timing is not so great, but thanks for still coming and sharing your work and attending the exciting talks. The goal of Research Trend Connect is to connect researchers worldwide, highlight new ideas, and support collaboration through this kind of discussion on recent academic work, because I know at conferences you're always talking about papers from 6 months ago. I don't want that to happen, right? So here we are talking about papers from last week or last month. So for this session, we are going to take a look at two research papers that are offering some fresh perspectives on federated learning. So let's get started. For the first presentation, the first speaker is Ertuğrul Keçeci.
It's okay, it's totally okay.
Yeah. So Ertuğrul has developed FedAlign. It's a framework for system identification tasks in federated learning. I think the core challenge here is the state representation alignment in state-space models. And FedAlign introduces some solutions for that. And they are kind of aiming to preserve local model dynamics and contribute to a coherent global model. So I am just summarizing this. I'm not sure if I'm representing it correctly. So please welcome Ertuğrul, who's going to introduce the work in a more exciting way.
Thank you, Professor. So can I share my screen?
Yes, please go ahead and share your screen.
Okay, can you see my screen now?
Yeah.
Okay. So check things. Okay. So I am Ertuğrul Keçeci from Istanbul Technical University, and today I will present our recent work on federated system identification, the FedAlign framework, which focused on aligning state representation across decentralized models. Here, what I will cover today, a quick intro to system identification and why federated learning makes sense in this context, and the problem caused by misaligned local models in FLCSID framework, and how we can use similarity transformation matrices to fix this. Then our proposed FedAlign framework and its two approaches to construct similarity transformation matrices. And finally, experimental results and key findings. In system identification, our goal is to model a system dynamics from input-output data. And one effective way is using state space models, since they describe the system through its internal states. As shown in the equation in this slide, the state space models relates inputs and outputs through a set of matrices. Now, if we have access to data from similar systems, like different units of the same robot, using them together could improve learning. That's where federated learning comes in. It enables us to train models in a decentralized manner without needing to share raw data. A perfect match for system identification across distributed systems. Here is the problem. The same linear system can be represented in different state space forms, like controllable canonical form or observable canonical form. These are mathematically equivalent, but structurally different representations. Now, imagine a federated learning setup where two local workers model the same system, but one learns in controllable canonical form and the other one learns in observable canonical form. The two state matrices you see in the slide represent exactly this case. They describe the same dynamics, but with different state representations. If the center server directly averages these models, the resulting global model won't preserve those dynamics, and it can even become unstable. So even though each local model is accurate, the aggregation fails because of the misaligned local models. To address this alignment problem, we consider similarity transformation matrices. They allow us to convert one state representation to another without changing the system dynamics. Now, let's go back to our previous example on federated learning with two local workers. If we use similarity transformation matrices, we can convert the observable canonical form representation into controllable canonical form representation. Then we perform the averaging in this common parameter basin. And once we do that, we get a global model that's now represented in controllable canonical form, as given in this equation, and which retains the dynamics of the local models. That brings us to FedAlign, the framework we propose for tackling the misalignment problem in the federated system identification. The core idea is this: before aggregating the local models, we first align their state representations using similarity transformation matrices to establish a common parameter basin. Once the state representations of local models are aligned, the center server averages them to obtain the global model. Then, instead of forcing every worker to adapt the representation in the common parameter basin, the center server converts the global model into the representation of each local workers. This approach guarantees that the global model reflects the true dynamics observed locally while maintaining the compatibility with each worker's own structure. In FedAlign, we propose two different approaches to calculate similarity transformation matrices. The first one is the FedAlign A. And this method, we use an analytical approach grounded in classical control theory. We represent the common parameter basin in controllable canonical form, and then we derive transformation matrices algebraically using the known structure of SISO or MIMO systems. And while this method is precise, it can be challenging for MIMO systems, where the controllable canonical form representation is not unique. On the other hand, FedAlign O offers more flexible alternative. In this method, in this approach, we don't force the global model into any specific state representation. Instead, we randomly choose one local model's representation as the common parameter basin. Then at the center server, we generate pseudo data and solve the least square optimization problems to estimate similarity transformation matrices. So to summarize, FedAlign A is an analytical data-free approach, while FedAlign O is data-driven and optimization-based. In our work, we evaluated FedAlign with different experiments covering both synthetic and real-world datasets for SISO and MIMO systems. We used prediction error minimization in local training, which is a widely used approach in system identification to estimate model parameters based on minimizing the difference between predicted and observed outputs. And we assess the performance using the best fit rate metric. And we also track the number of unstable global models generated by each method. Finally, to ensure the statistical reliability, we repeated all the experiments multiple times with different random seeds. Okay. Now, let's look at some results on the MR damper dataset. In the left figure, we compare FedAlign and FedAverage, both using just a single local iteration per round. And on the right, FedAlign still uses a single local iteration, while FedAverage is given an advantage with 20 local iteration. And even so, FedAlign still achieves higher accuracy with lower variability, which is a significant improvement. In addition to accuracy, we also analyzed how these methods behave during training. The left figure shows the evaluation performance when both methods run with a single local iteration. And on the right, FedAlign still uses only a single local iteration, while FedAverage uses 20 local iterations. And yet we can see that FedAlign steadily improves the local training performance from the beginning, while FedAverage exhibits significant drop at the initial communication rounds. But even though I only show the MR damper results, we observed similar trends across all the experiments. And even in some experiments, FedAverage generated unstable global models. And while FedAlign consistently preserved stability of the global model. So overall, the efficient alignment of the local parameter basins enables higher system identification performance, faster convergence, and enhanced stability of the global model. So that's all for me, and thank you for your attention. We're happy to take any question or hear your thoughts.
Yeah, thanks so much for being on precisely on time. And now we can turn to the next speaker for a brief session again. Youngjoon from KAIST. So his work is revisiting the stability of the vanilla Fed average algorithm. I think it's going to be quite interesting. So please, could you share your screen as well? And yeah, you did already. So can you maybe get started? Thank you so much.
Hello everyone, my name is Youngjoon Lee and I am a PhD student at KAIST in South Korea. And I will present the paper titled Revisit the Stability of Vanilla Fed Learning Under Diverse Conditions. Well, nowadays, a lot of researchers related to Fed learning publish FedEx like our method is SOTA and our method is the best, but they always put the FedAVG as a comparable benchmark method. This is because the FedAVG is the most stable method, and I think is after looking at the experiment, you guys will understand what I'm talking about. So nowadays, there are a lot of federal learning methods as shown in table 1, like from the basic is FedAVG, and the next one is maybe the FedProx and FedDin, FedCM, FedSem, FedGamma, and FedSP, and FedSmooth. And this kind of methods are using the advanced optimization techniques on the client side or on the server side. But unlike other methods, FedAVG doesn't use any kind of just do the mean stuff at the central server. So it's more simple and it doesn't have any other hyperparameters to consider than other methods. So in this paper, we validate the FedAVG achieves comparable convergence speed to recent federal learning methods across communication rounds and under diverse settings. And also we investigate the sensitivity of federal learning methods to the hyperparameter variations related to their methods. And as we can see at the experiment part that the FedAVG maintains the stable performance without requiring tuning, and it even gets more better performance than other recent methods. But we have to note that I didn't do all of the hyperparameter finding of other recent federated learning methods. I just do the common things for other methods as well. So I will just briefly talk about the process of the federated learning with the figure 1. So there's a lot of clients at the edge side, and there's one central server. Then the client trains its shared AI model with their own local data, and all of the edge device do it, and they send the learned AI models to the central server, and the central server aggregate and derive a global model and broadcast to all clients. And this kind of stuff is iterative when still it converges. So I just do write down the just general federal setting, like non-ID setting for problem for federal learning. So as this part two, I just write down the general federal learning process. So as I mentioned in the figure 1 process, is just written in English. That's the only difference. So these part are also just part of the figure 1.
Maybe can you come closer to the microphone because the audio is not great when you are away. Thank you.
Then I will just use the AirPods.
Okay, yeah, maybe that's better.
Actually, it's midnight in Korea, so my voice is a little bit sleepy. Please
Yeah,
understand
I
me.
understand.
Oh
I think
yeah, so
considering
yeah.
all of that, your voice is still very good.
Oh yeah, thank you. So as I mentioned in the figure 1, the server execute starts and this sends the global model, and the randomly sampled clients do some local learning and update, and the sends the updated model to the server, then server just aggregate and that kind of stuff. So it's the general stuff process of federated learning methods. And this part is not actually I wanted to talk just for writing a paper. And as looking to show the fed average is stable than other methods, I use the blood cell image classification dataset and the skin lesion classification dataset. And for the AI model at edge devices, I utilize the vision transformer, and also for other experiment, I utilize the vision transformer series as Swin or DIT stubs. And also I adopt the label school for the non-ID nature. And there is 100 edge devices, and every round the central server selects 10 devices at each round. And all of the stuffs are done by using the Intel Gaudi 2 AI accelerator because of the project. So for the first part of the experiment, I wanted to evaluate the stability of the different federated learning methods. And as shown in the figure 2, it's like test accuracy versus communication rounds for both data sets, which I've mentioned before. So we can see that the black line of FedAVG shows a comparable convergence speed and performance to other better learning methods. And this is not as well as shown in this experiment, FedAVG is better than other methods. But actually in the paper of this kind of recent federal learning method says that they have more better performance or convergence, but it's actually a cherry pick stuffs maybe. So if we just do a naive federal learning, then without do some hyperparameter tuning, the FedAVG will have more better performance or convergence round. And also we check the best performance by giving the model diversity. Well, in the first experiment, we just do the vision transformer, but in this experiment, we utilize more vision transform series like DEIT or David or Swim, and also it's not transformer based, but use the MOP mixer because it's more representative. So for like looking at the figure 3, well, the star means that the best performance, but like for the blood cell task, the fast gamma has the best in the most cases, but like in skin lesion task, the Fed AVG has 2 best performance. And as we can see in the both of the dataset results, Fed AVG has some relatively good performance, but like FedProx has some really unbalanced performance related to the model. So we can also check from this result that the federated learning performance is regardless of the AI model which the client will use. And also we have checked the hyperparameter selection because other recent federated learning methods highly rely on the key hyperparameters they have designed. So these are the hyperparameters for like Fed lambda is for the FedProx, which use in the client side, and FedIn for beta, the server side. So for like increase making smaller, so we can have a better, but not in all cases, but so for the hyperparameter for the 3 setting, the Fed gamma had the best in the IAD and the non-IAD for the blood cell task, and also in the skin lesion task. But this doesn't mean that Fed gamma is the best method of over other federated learning methods in this table, because I just done 3 grid hyperparameter search. And there's some time per round, but it highly depends on the chip we have done. You apply, so yeah, there can be some difference. And also, I just try to compare the conversion speed and the accuracy cost further learning methods just for ablation study. And as we can see that, well, definitely the recent further learning methods are good, but for just also considering the top one test accuracy, which is really useful and stable for it. And the conclusion is like this, and I just wanted to do this stuff because because when I have to do a further learning method, I have to design the learning algorithms like FedSpeed or Fed gamma, and also have to find the hyperparameter which makes the best performance. And I thought that was a really waste of time because I think it's not even possible to find the optimal hyperparameter because I'm not just doing this stuff. And also, the better learning objective is to do the learning on distributed clients. And but so the FedAV doesn't need to do something so we can get a consistent result by doing it. But if we utilize other federated learning as FedSpeed or FedSem or Fed blah blah, so then we cannot get a performance we want. So I think for the constrained resources like other developed countries, batteries will be more better to utilize than other state-of-the-art better learning methods. Thank you for listening to my.
Yeah, thank you.
Also, from my side, I should say that it would be highly appreciated if you can just spend a few minutes to just fill out the form that I'm just sharing the link on the chat now. And the thing is, since we are in the earliest steps and we want to just enter the market and see how the potentials and what we can do with that. And the other thing is that if you have some ideas later, not right now, that would be great if you can just share it with us even through the LinkedIn page, or like you can just directly contact me, and then we can just see how we can improve ourselves and make the sessions more engaging and also attractive for the future sessions, I would say. Yeah, this is all from my side.
Yeah, thanks. And yeah, with this, we can probably close the first session, the Federated Machine Learning session. And I wish to thank Youngjoon and Ertuğrul for joining and presenting your work. Thank you so much.